So in this video, we're going to be looking at calculating enthalpy changes. Now, enthalpy changes itself can actually be calculated directly using experiments. However, sometimes this isn't always going to be possible for the following reasons: of the activation energy that could be too high and that reaction won't actually happen in laboratory conditions. If we were to look at, let's say, the rate of reaction, the rate might be too slow, so the reaction might actually take too long. If you were to look at the reaction itself, right, we're assuming that the reaction is going to be isolated, where we've got only one reaction taking place, but we could end up with multiple reactions taking place, more than one reaction taking place, and so we can form more than one actual product itself as well. Now, let's say if we were to look at calculating enthalpy changes indirectly, right, we can do this using a variety of different ways. There's two in A level that you need to be aware of in year one, and one of them involves you taking something called average bond enthalpy data, which we'll look at in another video, and that is basically when you deal with bond energy calculations, going from reactants to products, your bonds broken versus your bonds formed itself. If you were to look at another method, right, a new one that you'll come across at A level, we look at standard enthalpy changes of combustion or formation data and forming Hess's law cycles to calculate the actual enthalpy change itself, right? So yeah, let's look at how we can actually calculate enthalpy changes and set up an experiment. If we were to look at, let's say, a reaction involving two solutions reacting together, such as HCl and, let's say, sodium hydroxide, we would need two pieces of information to calculate enthalpy change. The first one is the number of moles of what's reacting, which for solutions, you can find using the formula of N is equal to CV from quantitative chemistry. You also need to be able to measure the temperature change from the start of the reaction to the end of the reaction itself as well. And so let's say if we were to deal with the apparatus, it's going to be quite simple. You've done it before at GCSE in a required practical. You take a polystyrene cup and you place, let's say, a known amount of HCl into your actual polystyrene cup itself. The order doesn't really matter as long as it's one of the solutions. And what you do is you measure the temperature, right? The initial temperature is what we're going to call it, of the actual solution itself as well. Now, once you've measured the temperature, let's say if that temperature is going to be 25 degrees Celsius, you then add in your solution of, let's say, sodium hydroxide, and you give that a mix so that your solutions are going to be evenly distributed throughout the actual polystyrene cup itself. Now, once that's done, right, you wait until the temperature stops rising. So you continue to measure the temperature at intervals of, let's say, a minute or 30 seconds or whatever it might be. And then once the temperature reaches its peak, you've got the maximum temperature, which in this case, let's say it's going to be 30 degrees Celsius. And what you can actually get from that is something called delta T, which is a change in temperature. And that tells us a lot of information and gives us information to calculate a value of the energy absorbed or energy released. And then you can actually calculate the enthalpy change itself. In this case, right, we know temperature is increasing. We know the reaction is going to be exothermic itself because energy is released to the surroundings. So we expect to have a negative enthalpy change. Delta T in this case is going to be equal to 5 degrees Celsius, and it doesn't matter if we're dealing with degrees Celsius or Kelvin, because the change in temperature is what matters the most. So let's say if we did have Kelvin, let's say if we had 298 Kelvin, right, because that's going to be our temperature in kelvins, we can actually measure, right, the final temperature as being a value that is going to be 303 Kelvin itself, and so the change in temperature is still going to be, right, 5 Kelvin. The number is what's important over here. 5 degrees or 5 Kelvin is fine. Now, when dealing with this reaction itself, right, we're assuming that none of our energy is being lost to the surroundings itself, and we're measuring the exact temperature change of the actual reaction. That's not going to be true, because as temperature is going to increase, right, of the solution, we know heat energy is going to be lost to the surroundings, and so the temperature that we actually record for the final temperature is not going to be accurate. Now, in reactions involving solutions, it's not that much of a problem, but let's say if we were to deal with calculating the enthalpy change of combustion of, let's say, an alcohol or some sort of a organic compound. Well, let's say if we were to take ethanol, which is going to have the formula of C2H5OH, just like before, we can actually calculate the number of moles of this fuel itself, but then to calculate the temperature change is a bit different over here because the apparatus is going to be different. And what we're actually going to do is we're going to take a spirit burner, right, which is going to contain our alcohol itself, right, and we're going to have a tip on there, right, that we're going to light, and that tip, right, is going to catch on fire, and that fire, right, is going to release energy, and we're going to end up, right, in this combustion reaction, heating, right, a beaker of water on an actual tripod itself. Now, to be very accurate, right, what we normally use is something called a copper calorimeter, because it's a good conductor of heat itself. And we have that, looks like a mug pretty much made out of metal, copper metal, with a lid on it, and a stirrer as well to actually stir the solution, and then a little hole in there, right, to put our thermometer in. Now that is going to be on top of a tripod, right, and then we're going to have a heat proof mat at the bottom as well. And when we look at this apparatus, right, again, we can end up with the same issues as before, where heat can be lost to the surroundings, because we can't guarantee that all of the energy released from this reaction is going to heat the water up itself. But again, we're looking at the temperature change in this case of our water, because we can't actually measure the temperature change of the fire directly itself, right? So yeah, let's say if we were to look at this reaction, how would we actually calculate the number of moles? Well, we would look at, right, the mass of the spirit burner before the reaction versus after the reaction, and what will happen is, right, is there will be a change in mass, and so we can actually calculate the change in mass, which is going to be the mass of our ethanol reactant itself. And then what we can do is we can take the MR of ethanol from the periodic table, and we can actually calculate a value for the number of moles. And then again, the change in temperature, this is the important bit, is going to be of water itself as well. So yeah, let's say if you've calculated then the change in temperature and the number of moles for either two of these reactions itself, we need to use the following equations over here to be able to calculate enthalpy change. Now in some cases it might be a lot simpler of how I've shown it, in some cases it might be a bit more complicated, but the whole idea and theory and how we approach these calculations is going to be the same. So yeah, the first thing that we need to actually do is calculate the energy released or absorbed by this reaction itself as well. And to do that, right, to calculate a value of Q, which normally has the units of joules itself. Now the first thing that we're going to need is the mass of the solution or water being heated itself as well, and that's going to be in grams. Now let's say if you're dealing with HCl or sodium hydroxide, right, let's say if we're dealing with this first experiment over here, you would take, right, the mass of the solutions of HCl and sodium hydroxide. Let's say if I've got 25 centimeters cubed of HCl and 25 centimeters cubed of sodium hydroxide, right, I need to make the following assumption that 1 centimeter cubed is equal to 1 gram when dealing with water or solutions. And so I can say, right, overall the mass of the solution is going to be 50 grams, because I've got 25 by 25 is 50 centimeters cubed. 50 centimeters cubed is going to be equal to 50 grams of solution actually being heated itself. If I'm dealing with the combustion experiment, I'm going to take the volume of water in my actual calorimeter itself over here, and let's say if that volume of water was 100 centimeters cubed itself, I know that the mass of that is going to be 100 grams because of the following assumption over here that we made earlier on as well. So yeah, in that case, right, we can work out the mass in grams. We can then take a constant which is actually provided on your data sheet, which is going to be the specific heat capacity of water, which is going to be 4.18, and the units for that is going to be joules per gram per Kelvin itself. And then if I were to look at the temperature change, right, if I'm looking at temperature change, doesn't really matter what units that you use, right, you can go with either degrees Celsius or you could go with Kelvin as well, because the value is going to be the exact same as well. Now the next step is to actually take the number of moles of a substance that's actually going to be reacting. And let's say if we're dealing with experiment 1 over here, where we're taking two solutions, we'd find the number of moles of sodium hydroxide, the number of moles of HCl independently, and then we would look at which is the limiting reagent. And so we would use that as our number of moles of what's actually reacting, and so we can continue with our calculation. But what if we're actually dealing with this experiment over here, where we're using the spirit burner? Well, we won't actually work out the number of moles using the same equation, N is equal to C times by V, but instead what we would actually do is find the number of moles by taking the mass of our actual alcohol itself and then dividing by the MR of the alcohol or whatever organic compound that you're actually dealing with as well. Now the final step involves us first of all converting Q into kilojoules, and to do that we're going to divide by 1,000. To go the opposite way, you need to times by 1,000, and then we need to be able to divide by the number of moles of what's reacting, our limiting reagent, and we end up with enthalpy change itself as well. Now when dealing with enthalpy change, right, let's say if we're dealing with a standard enthalpy enthalpy change of combustion, we know that this value here is going to be different to this value over here, right? The value we actually calculate, which is going to be, let's say if we're looking at the standard enthalpy change of combustion, the experimental value, we will call this just the enthalpy change of combustion. And there's a reason for that, and it's because this value is going to be less exothermic compared to the calculated theoretical values for three reasons that we need to be aware of. One of them being that heat could be released to the surroundings. So let's say in this apparatus over here, which is used to calculate the enthalpy change of combustion, heat, right, is not going to heat the water completely. Instead, right, we can actually end up with heat being released to the surroundings, as we mentioned before. We can end up with incomplete combustion as well, right? We're assuming that we're going to have 100% complete combustion and an excess supply of oxygen, but that's not always the case. We can end up with incomplete combustion or an incomplete reaction, in other words. And another thing is we can actually have non-standard conditions as well. We can't guarantee that within the actual room that we're conducting our experiment that we've got standard temperature, which is going to be 25 degrees Celsius or 298 Kelvin, and then standard pressure as well, which is going to be 100 kilopascals or 100,000 pascals itself. Now let's say if we're dealing with the first experiment over here in terms of the enthalpy change, let's say in this case it's going to be the standard enthalpy change of neutralization. Again, we can't actually show this little London Underground symbol over here for standard conditions because we can't actually have that. And again, you know, instead of having incomplete combustion, we're just going to have an incomplete reaction. What if we didn't leave the reaction long enough to react itself? Again, we're going to have heat released to the surroundings because we can't guarantee, right, that the solution is actually going to be heated. What if heat escapes this polystyrene cup from above? And polystyrene itself, you know, it's an insulator, which is really good, but heat can still be transferred through it as well, right? So yeah, how can we actually calculate enthalpy change? Let's actually look at an example. I've got here pentanol. It's liquid and has a molecular formula of C5H10O, and a student does an experiment to measure the enthalpy change of combustion delta HC of pentan-1-ol. The student found that combustion of 1.54 grams of pentan-1-ol changes the temperature of 180 centimeters cubed of water from 22.8 degrees Celsius to 75.3 degrees Celsius itself. Now we know straight away that this is going to be exothermic in terms of a reaction because temperature is going to be increasing. We're told the specific heat capacity of water as well is going to be 4.18 joules per gram per Kelvin, but just remember this value is actually given on your data sheet as well, and that's in every exam. Whereas to calculate the enthalpy change of combustion, in this case delta HC of pentan-1-ol in kilojoules per mole. So the first thing is I need to be able to calculate a value for the energy release in this exothermic reaction, which is going to be equal to Q is equal to MC and then delta T itself. And I'm going to sub in my values, so I know first of all they're heating 180 centimeters cubed of water. Remember, we're not dealing with this mass value over here that would not be incorrect. That's the mass used to calculate the number of moles of your substance reacting, because this is a combustion experiment. And so, right, I'm going to take 180 centimeters cubed, bearing in mind that 1 gram is going to be equal to 1 centimeter cubed. I'm going to say that I've got 180 grams times in, right, 4.18, the specific heat capacity of water, and then we're going to times, right, by our change in temperature, which in this case is going to be 75.3 subtracting 22.8 degrees itself. We don't need to convert into Kelvin because we actually get the same number, and so in doing that I actually end up with a value that's going to be 52.5 degrees Celsius. I'll put that in my calculator, and to three significant figures I end up with 3,9, and then it's going to be 5,000, and that's going to be joules as well. Now the next thing is I need to be able to calculate a value for Q in kilojoules. So to do that, I'm going to take my value of 39 and then 5,000, and I'm going to divide that by 1,000, and what I end up with is a value of 39.5, and that's going to be kilojoules itself. Now I need to find the number of moles of propan-1-ol, which is C5H12O itself, and to do that I'm going to do mass divided by the MR, and so that's going to be the mass of this, which is going to be 1.54 grams, and then divided by the MR, which I can calculate as being 88, and that's going to give me a value of 0.0175 moles itself. So I've got a value for the number of moles over here, I've got a value for the energy released over here as well, and so to calculate a value for the enthalpy change of combustion, what I'm going to do is I'm going to take my value of Q and divide by the number of moles. So I'm going to take 39.5, divide that by 0.0175 itself, and so that's going to give me a value that's going going to be 2, 2, and then 6, 0, and it's going to be kilojoules per mole. But we're still not finished yet. We need to think back, right? Temperature's increasing. We know it's exo, as we mentioned before, so we need a negative symbol there as well to show it's an exothermic reaction. And so, right, in that case, that's how you can get 4 easy marks, right, in calculating the enthalpy change of combustion itself, right? Another follow-up question could be, okay, so why is this reaction not going to match the actual value, which is going to be so and so? Well, we can say again, we've got incomplete combustion or incomplete reaction, we've got non-standard conditions, right? And then we could also say that heat could be lost to the surroundings itself. So moving on then, right, feel free to pause the video and have a go at this example. Just be aware that you're dealing with solutions this time and you're trying to calculate the enthalpy change of reaction as well. So you're looking at this question then, right, we've got aqueous lead nitrate, and that's going to be reacting with aqueous potassium iodide itself. We've got here a balanced equation where we've got a 1:2 ratio in terms of our reactants, which is very important because, again, we need to look at the limiting reagent itself, and we may need to divide or times something by a number like 2 or 3 as well. Now, in this case, right, we've got a student and they carry out an experiment to determine the enthalpy change of reaction of this reaction. The student adds 50 centimeters cubed of 1.5 mole per decimeter cubed of lead nitrate to a polystyrene cup and measures out 50 centimeters cubed of solution of potassium iodide, and that's going to be in excess, which is very important because we know, right, we're going to be dealing with lead nitrate in terms of the number of moles. Now they measure the temperature of both solutions and add potassium iodide to the polystyrene cup, stir the mixture and record the maximum temperature itself as well. Now you can see here they've got temperature change going from 19.5 to 30 degrees Celsius. And to begin with, the first thing that we're going to do is actually calculate a value for Q, which is going to be equal to, again, MC delta T, just as before. And we know that the mass in this case, because we're dealing with a polystyrene cup, we're adding in, right, 50 centimeters cubed, followed by another 50 centimeters cubed. The total volume is now going to be 100 centimeters cubed for our solution itself. We're not dealing with water over here, but we can make the same assumption that we've got 100 grams for every 100 centimeters cubed. And then what we're going to do is we're going to times by the specific heat capacity of the solution, which is 4.18, and then we're going to times that by the change in temperature, and the change in temperature in this case is going to be 30 degrees Celsius subtracting 19.5 degrees Celsius, and that's going to give us a value of 10.5 degrees Celsius for the temperature change itself. And so that's going to give us, right, if I put that in my calculator, a value of 4389, and that's going to be joules. To convert that into kilojoules, right, I'm going to do 4389, divide that by 1,000, and I end up with a value that's going to be 4.389, and that's going to be kilojoules itself. To find the number of moles, right, in this case we're dealing with lead nitrate, I'm going to do, right, concentration times by volume, and so that's going to be, right, 1.5 times by 50 over 1,000. And the reason why we're actually dealing with 50 centimeters cubed is because we've got that as our volume for the lead nitrate solution itself as well. So I do that, I put that in my calculator, and I end up with a value of 0.075 moles itself for lead nitrate. And so I can actually calculate a value for the enthalpy change of reaction, which is going to be equal to Q over N, which in this case is going to be 4.389 divided by 0.075, and so I end up with a value of 58.5, and that's going to be kilojoules per mole. Again, we're not finished here. The temperature is going to be increasing, so we know it's going to be exothermic because that's released to the surroundings, and so it's going to be negative as well. And so we've got here another 4-mark question completed and done as well. So moving on, feel free to have a go at this question over here. Right, a bit more challenging because you've got to work backwards. Pause the video, and once you're ready, feel free to resume and we'll go through it together. So yeah, in this question, we've got enthalpy changes of combustion. Again, we're going to be dealing with 2 separate masses in this case, and we've got a student that carries out an experiment to determine the enthalpy change of combustion for cyclohexane, which is going to be C6H12. Notice how we can actually calculate an MR from that as well. And in the experiment, we're told 0.525 grams of cyclohexane are actually going to be burnt, and so we can calculate the number of moles from that. We're also told that the temperature of 200 centimeters cubed of water increases from a temperature of 21 degrees Celsius, and the student calculates the enthalpy change of combustion, delta HC, of cyclohexane as being minus 2680 kilojoules per mole itself. We're asked to determine the maximum temperature of water being heated in the experiment. So again, right, we're going to be working backwards in this case, so we need to start off by thinking about our equation. delta H, and it's going to be combustion, is equal to Q over N. And how we can actually rearrange this? Well, to rearrange this, we need to be able to find Q in this case so that we can actually find our value for delta T, and hence we can find our maximum temperature itself. So what we actually end up with is a new equation times in both sides by N. So in that case, Q is going to be equal to delta H combustion times by the value for the number of moles, and so that's going to be the enthalpy change of combustion, which in this case is given to us as minus 2680, and that's going to be times in by the number of moles of cyclohexane. And so to find the number of moles of cyclohexane, what I need to be able to do is take the mass and divide that by the MR itself, and so that's going to be equal to 0.525 divided by the MR, which in this case is going to be 84. And so I end up with a value of 6.25 times 10 to the power of minus 3. That's how many moles I've actually got. And so I'm going to do minus 2680, and that's going to be times in by 6.25 times 10 to the power of minus 3. And then we end up with a value of 16.75, and that's going to be kilojoules itself. Now I've actually got rid of the minus sign over here because we don't actually need it, and it's easier to work with this number of 60.75 rather than minus 16.75 itself as well. We already know energy is being released, we know it's an exothermic reaction, and we know the temperature is going to increase as well. Yeah, so moving on, right, we've got these two marks over here. We now need to be able to find a value, right, using Q equals MC delta T. We need to now rearrange this to find a value for delta T. So what we end up with is dividing both sides by MC. So we know delta T is going to be equal to Q over and then MC itself. And so, right, what I actually end up with is my value for Q, which is now going to be converted into joules, which is going to be 16.75 times by 1,000. And then we're going to divide all of that by the mass of the solution or water being heated, which in this case is 200 centimeters cubed. And then we're going to times that by the specific heat capacity of water. And so what we should end up with is a value of 20.0 itself, and that's going to be in degrees Celsius, right? Doesn't really matter in this case because it's temperature change, could be Kelvin, could be degrees Celsius, it's not that important. So yeah, what if I were to find the maximum temperature, right? So in that case, what I would need to do is I would need to take 21, and then I would need to add on, right, 20 degrees Celsius, and so what I end up with is 41 degrees Celsius. So I know my final temperature must actually be 41 degrees Celsius in itself.